Solving quadratic equations by completing the square may be new for you, but we're going to first start with just using the square root property, which is pretty straightforward. I think you may have seen it before. The one thing to be careful with is not to forget the plus or minus. So at the square root property, if you have a squared equals to a number, then a is equal to plus or minus the square root of that number. So don't, again, forget the plus or minus. Got an example here. If x squared equals 20, our first example here, then x is equal to plus or minus the square root of 20. And the square root of 20 we can simplify, 20 being 4 times 5, and 4 being a perfect square. Square root of 4 is the 2, and then the square root of 5. Now be careful here. This is the positive or negative of the square root of this number. So it's the positive 2 square root 5 and the negative 2 square root 5. So I'm going to make that a little more legible. It is not 2 plus or minus the square root of 5, which is a very different decimal approximation than these two. So don't do that. If we use the square root property, it is important that we first get the x squared isolated like it was here. So in this problem here, before we do the square root property, we first need to do a little algebra. We can make this 5x squared equals positive 55, adding 55 to both sides. Then we can divide both sides by 5, giving us x squared equals 11. Now we're in a position to apply the square root property, and x is simply plus or minus the square root of 11. 11 is a prime number, it cannot be simplified, so you could also write this as x equal the negative square root of 11 and the positive square root of 11. Okay, so a couple variations on this one. Here, the left side is squared equal to 18, so we can apply the square root property because it's the whole thing being squared, so we can, essentially what we're doing is square rooting both sides. So this becomes x plus 2 equals plus or minus the square root of 18. We can clean this up a little bit, so let's do that first. 18 being 2 times 9, or 9 times 2. 9's a perfect square, we can square root it. So this would be 3 square root 2, square root of 9 being the 3. And then to get the x isolated, we can subtract the 2 from both sides. And this will give us x equal negative 2 plus or minus 3 square root 2. Or you could also write this in a long notation, negative 2 plus 3 square root 2, and negative 2 subtract 3 square root 2. Okay, do you want to try the next one? Okay, how do we do there? So again, essentially what we're doing with the square root property is square rooting both sides of the equation. So that cleans up the square here, leaving us with just 2x subtract 1 on the left side, and then plus or minus the square root of negative 9 on the right-hand side. So the square root of negative, of course, we know is an I, and the square root of 9 is a 3. So the square root of negative 9 is 3i. Then we can add 1 to both sides of the equation, giving us 2x equals 1 plus or minus 3i. And then we can divide both sides by the 2. So x is 1 plus or minus 3i over 2, which you could leave in that format. Or again, you could split it up. 1 plus 3i over 2, 1 subtract 3i over 2. And even that you could split up 1/2 plus 3/2 I, and 1/2 subtract 3/2 I. On the test, I would be fine with any one of these 3 formats here for writing the solution. Okay, so now we're going to go into solving quadratic equations by completing the square. So those last 2 examples, these 2 original problems back here, are in what we call completed square form. So the process of taking a standard quadratic equation, ax squared plus bx plus c equals 0, to the form dx plus e quantity squared equals f, and then solving by the square root method that we just did, is called solving equations by completing the square. Our result would be the same if we use the quadratic formula, which we'll be coming up to next, and most students have a preference for whether they're completing the square or using the quadratic formula. So we'll show you both. You can decide which one you like better. So in order to complete the square, we're going to need a magic number. Now the magic number is going to be different for every problem, but this process for finding it's the same. So with the magic number, we take the coefficient of x, divide it by 2, and square the result. Why is this a magic number? The magic number is going to give us a quadratic that we can factor into a perfect square. So let's go through a couple here. So first example, I just have x squared plus 8x plus what? What I want to do is take the 8, that's my coefficient of x, divide it by 2. 8 divided by 2 is 4. So I divide it by 2, and then I want to square the result. So 4 squared is 16. That's my magic number for this one. Why is it a magic number? Because if I now factor the result, x squared factors to x times x, 16 factors to 4 times 4, and to get a plus 8x, I need a plus plus, so this is factored into a perfect square. So that one comes out nicely. These can get a little ugly if your coefficient of x is an odd number, as is this one. But we're going to do the same thing. We're going to take the coefficient of x, which in this case is a -5, divide it by 2, and square it. So that gives me 25 over 4. So I'm going to add that here, and that gives me something that will factor to x subtract 5/2 squared. The next one's a little trickier because of this 2. For this magic number to work, I actually need my leading coefficient, my a value, to be a 1. So what I'm going to do here is first factor that out. And then, now that my leading coefficient is a 1, I can take the 2. Half of 2 squared would be 1 squared, would be 1. And then my 2 sitting out here, this will now factor to y plus 1 times y plus 1, or y plus 1 squared. Okay, so how can this help us solve a quadratic equation? So the process we're going to do is first, whatever's a constant there to begin with, kick it over to the right-hand side, get it out of the way. Now we're going to add our magic number to both sides of the equation. So again, as long as we're doing the same thing to both sides of the equation, that's legitimate. So half of 8 squared is going to be our magic number. Oops, that should be an equal sign. 4 squared, which is the 16. So we'll take our x squared plus 8x plus 16, add that to the left side, and then to balance it, we also add it to the right-hand side. This side now factors to x plus 4, x plus 4. This side simplifies to 17. So now we have a quadratic equation in completed square format, and we can now solve by the square root method. That gives me x plus 4 equals plus or minus the square root of 17. And then to get the x by itself, we need to kick the 4 over to the other side, so we subtract 4 from both sides, and we get -4 plus or minus the square root of 17. And we have solved by completing the square. This one again gets a little messier just because we've got fractions, but not too bad. Again, the constant that comes with the equation, we move to the other side. Our magic number, take the coefficient of x, divide by 2 and square. That gives us 25 over 4. So we add that to both sides. The left-hand side will factor to a perfect square. You can do that in 2 steps as I did over in this first example, or cut straight to the chase. I'll leave that up to you. Over on the right-hand side again, since we do have fractions, we're going to have to get a common denominator. So I can multiply this one top and bottom by 4, turning that into 8 fourths. It's the same thing as 2 plus 25 fourths. Let's see, then I have x subtract 5 halves squared equals 8 plus 25 is 33 over 4. And now I'm in completed square form, and I can solve by the square root method. So square rooting both sides, I get x subtract 5 halves plus or minus the square root of 33 over 4. And then I can bring the 5 halves to the other side, adding 5 halves to both sides. I could clean this up a little bit. I can't do much with the square root of 33, but the square root of 4 is 2. And so again, final result. Now this example, we've got this leading coefficient we need to worry about. So we could either factor it out or divide it out. Two ways to say the same thing. We'll need to again kick the 3 over to the other side. I think I'll start with going through dividing the entire equation by 2. So that will give me y squared plus 2y plus 3 halves, and of course 0 divided by 2 is still 0. So we did the same thing to both sides of the equation. Now I can move the 3 halves to the other side, completing the square on the left-hand side. Whoops, that should be a negative 3 halves. There we go. I need my magic number, so taking the coefficient of the y, half of it squared would be 1 squared, or 1. So I'm going to add 1 to both sides of the equation, so that this will now factor to the y plus 1, or simply y plus 1 squared. Again, you can skip that step if you prefer to jump straight to here. On this side, I've got a fraction, so I may as well get some common denominators. Taking the 1 to 2 over 2, so that gives me a negative 1 half. The negative 3 plus 2 is negative 1. So when I use my square root property, I am going to be taking the square root of a negative. I know this is going to turn out to have a complex number for its solution. So square rooting both sides. And then I can bring the 1 over by subtracting 1 from both sides. Square root of a negative is going to give me an I. And I would be fine with you stopping here. I will warn you, when checking answers in the back of the book, they are going to rationalize the denominator because they don't like to leave fractions inside a square root, and they don't like to leave the square root in a denominator in particular. So what they're going to do, and this is entirely optional, is they're going to take this sort of answer so the square root of 1 half is the square root of 1 over the square root of 2. They're going to multiply top and bottom by the square root of 2. You can call this rationalizing the denominator in order to get a denominator that does not have a radical in it. Square root of 1 times the square root of 2 is, of course, the square root of 2. Square root of 2 times the square root of 2 is the square root of 4, which is 2. Again, you don't have to do that. You can stop right there. You get to trigonometry. We'll talk more about that. Example here, a story problem. Say we have A equals P1 plus R to the T. So this is a simple interest problem for a principal being sitting for T years in an account paying R%. So say I have a retirement account that drops from 15,000 to 9,000 in the past year. What interest rate would I need for my account to recover in the next 2 years? So what I'm asking here is I want to take my $9,000 and have it grow back to $15,000 in T equal 2 years. And what I'm looking for is what R would make that happen. What interest rate would I need? So starting with my formula, the amount I want to end up with is $15,000. What I'm starting with is the $9,000 in my account. I'm looking for R, and because I want it to recover in the next 2 years, I'm going to have a 2 here. So to solve, we are already in completed square format, but I do need to divide by the 9,000 before I square root both sides to get this side of the equation as one thing being squared. So dividing by 9,000 would give me, let's see, 15 over 9. That should simplify to 5/3. Now I'm ready to square root both sides. So the square root of 5/3 equals 1 plus R. And then I can subtract 1 from both sides. So that gives me R equals 1 plus square root of 5 over 3 and 1 subtract square root of 5 over 3. So I'm getting two solutions, but remember with story problems, not all solutions really make sense. So if I go to my calculator, 1 plus the square root of 5 over 3 is 1.745. Whoops, I'm sorry, that should be a -1. That didn't make sense. Okay, let me double check that on my calculator. So that's giving me negative 0.2546. Okay, had a calculator error there. So the -1 plus the square root of 5 over 3 is going to give us 0.29099, so about 0.291. The -1 subtract the square root of 5/3 is going to give us -2.291. So my interest rate cannot be negative. So what I need is an interest rate of about 29.1% for that $9,000 to grow back to $15,000.